Okay, so welcome back to my channel and welcome back to the Regression Using R video series. Today we're going to be talking about how to add interaction terms, and you might also have heard this referred to as moderation. It's pretty much the same thing. And so as usual, what we'll do is we will start with some applied examples and we'll go over how to, run the code in R and basically do everything we need to from a coding standpoint. And then we'll go over in the second half of the video how to write up and interpret the results. Okay, and so we'll go ahead and get started with the interaction terms, and we will start with some coding. Okay, and here we are. And so here's a list of the packages that we'll need to follow along. We won't use all of these for today's lesson, but basically you need to have all of these for the previous videos anyways, so you might as well go ahead and load them and install them. And so I'll go ahead and let you take a look in case you need to make sure you have everything. And yeah. And so, as always, the code and all of the data files that we're going to go over today can be found on my GitHub page, and that link is in the description. I highly encourage you to check it out. It's really simple. You just click on the link, you go to the regression using R, and then navigate to the data files, and then you'll also see the .r files, and those are the script files that you see right here. And so you can copy and paste them, or you can download them, and then you can follow along, or you can basically just use this script to run your own analyses using your own data set. So definitely check that out. It's super simple, and I would really appreciate it. Okay, and so today we're actually going to be working with a new data set. Previously, we had been working with a data set where we were predicting employee turnover from a variety of variables. And today we're actually going to be working with a data set that comes from the textbook Regression and Other Stories. I've put a link to the author's GitHub page right there. This is an excellent textbook and I highly recommend it. It basically uses code to teach statistics and regression specifically. And they also go over, from a really simple standpoint, how to run pretty much any analysis using code. And they also cover Bayesian regression too, which I'll go over in future videos. But anyways, that's a link to their GitHub page. You can also get the code and the syntax for today from my GitHub page, but definitely check them out if you get a chance. And so again, today we'll be looking at a data set where we are going to predict the child's IQ, which is KID score, from mother's high school and mother's IQ and mother's hours worked, so mom work. And then for the mom high school, by the way, that's coded 1-0, whether or not they graduated from high school. So 1 means the mother did graduate from high school, 0 means they did not. Then we have mother's IQ, of course, and then again, this is the number of hours that the mother worked. And then we have the age as well. Okay, and the first thing we're going to do is we're going to do some basic housekeeping. We're just going to make our first categorical variable a factor. And so I'm going to do that. And then also we need to mean center our continuous predictors. If your variables in your data set are not already mean centered, this is how you can mean center the continuous variables. It's important to note that there's a lot of debate about whether or not you need to mean center predictors. It makes absolutely no difference for the results of the regression. You do not have to mean center your predictors. Some people say you do when you're doing interaction and moderation. You absolutely do not. The reason why I choose to mean center them is because it makes the results easier to interpret, and we'll see that when we go over the results, but you absolutely do not have to mean center your variables. That's just a personal choice, and again, it's just because it makes the interpretation make a little bit more sense, but from a practical standpoint, you do not need to do so. If you want to do so, here's how you would do it. You would just say scale whatever variable you're interested in, and then you say scale equals false because you don't want it standardized, you just want it centered. So we'll go ahead and run those two lines because I do want to mean center my variables. And then we'll go ahead and start with looking at a categorical interaction. So we're going to predict child IQ from mom high school, whether or not the mom went to high school, the mother's IQ, and then the interaction between mom IQ and mom high school. And so when you're fitting interaction or analyzing interaction terms, it's best to start with the main effects first. So in other words, fit a model without the interaction first. So we'll go ahead and set model 1 as a linear model predicting child score from mom high school and a centered version of mom IQ. And notice we do not have an interaction term yet. We'll go ahead and fit that model. Oh, looks like I made an error up here. Sorry about that, I had forgotten to set up the IQ center variable. So we'll go ahead and try that again. There we go. And so we'll run a summary of our model. Again, this is without the interaction term. And the reason why you have to do this is that when you run the model with the interaction term, the main effects of your variables are not interpretable. And we'll see that when we go over the results of an interaction term analysis. But if you want to actually analyze the main effects of your variables, so the main effect of the mother going to high school and the main effect of mother's IQ, you need to do that without the interaction term first. And so here's the summary of that model with just the main effects. And we'll go over the interpretation in a minute. And then here is the effect size. So we see the standardized coefficients and the 95% confidence interval. And now we'll add the interaction term. So as you see, we're setting our new model, M1B, and we're predicting kid score from the mother high school and the mother's IQ. But now we have added this star right here to specify that we want an interaction term. So we'll go ahead and run that. And now I forgot to add this. We'll take a look at this real quick just to see what it looks like. And so as we can see, now we have at the bottom here, we have this interaction term between mother's high school and mother's IQ. And again, that's the centered version of mother's IQ. And so as we can see, the interaction term is significant. And here's our slope coefficients and our standard errors and so on and so forth. And then we can also get the confidence interval for the standardized regression coefficients. And there we go. There's the standardized estimates and their confidence intervals. And again, I'll go over how to interpret these in the second half of the video. And so now we might want to actually probe the interaction and get what we call simple slopes. So what you do is you say interact plot, the name of your model, the model where you included the interaction term. You fill out the variable that you want to be the main predictor, so in our instance IQ, and then you add in mod x equals the name of the variable that you want to serve as the moderator. And what I mean by that is we have to pick one variable that we want to specify as the main predictor and another one that we want to see that has some influence on the effect of that main variable. And so what I mean by that is if we say that the moderator is mother's high school, what we're saying is that we think the effect of the mother's IQ on the child's IQ varies depending on whether or not the mother went to high school or not. And so you specify the categorical variable as your moderator. And again, this is saying that we think that the effect of the continuous variable IQ varies based on the level or the value of the categorical variable, which is high school. So we think that the slope of mother's IQ is going to vary based on whether or not the mother went to high school or not. So again, we specify the moderator as our categorical variable and the predictor as our continuous variable in this instance. So we'll go ahead and run that. And we see a plot right here. And this shows us the slope of IQ predicting child IQ score. So sorry, it shows us the slope of mother's IQ predicting child IQ, and it shows us for both levels of mom high school. So the blue line represents the slope for the mothers that did not go to high school, and the orange line represents the slope for when the mothers did in fact graduate high school. And as we can see here, the slope is steeper when the mom did not go to high school. So basically there's a stronger predictive relationship between mother IQ and child IQ when the mother went to high school. And that slope is still positive, but it's less positive when the mother did go to high school. So just to make sure I didn't confuse what I said, again, when the mother did not go to high school, the slope is stronger. So in both instances, we still see that the mother's IQ is a positive predictor of the child's IQ, but the magnitude or the degree to which that is the case varies based on mother's high school. And specifically, if the mother did go to high school, that slope is less. And then we can also run our regression diagnostics. So we'll say OLS plot, diagnostics, and then the name of our model. And then this is going to give us a whole bunch of regression diagnostics. And I will go over some of them on the PowerPoint, but as you can see, it prints out a whole bunch of them, and you just have to specify this once, and it gives us a whole bunch of cool stuff. And let me go ahead and close out of the rest of those real quick. Okay, and so that was how we do the categorical predictor. So again, this is when you have one categorical predictor moderating the effect of your main continuous predictor. And now we'll look at when you have two continuous predictors. So we're going to have a continuous predictor moderate the effect of our main continuous predictor. So in other words, in this instance, now we're going to look at child IQ predicted from mother's work hours, mom's IQ, and the interaction of mom's IQ and mom's work. So what we're saying is that we think the effect of the mother's IQ upon the child's IQ varies depending upon the number of hours that the mother works, okay? And this time, mother's works, the moderating variable, that's the number of hours the mother works, that's a continuous variable. And as before, you fit the main effects first. So we're going to say M2 is a linear function of the child IQ score as a function of the mother's work, the centered version, and the mother's IQ score, the centered version. And again, when we go over the results in the PowerPoint, you'll see why I'm using the centered versions, but you don't have to strictly. And so we'll fit this main effects model first. Notice how there's no interaction term in that code. We'll look at the summary. And as we can see, the main effect of mother's work is not significant. So when we control for IQ and we don't include an interaction, the number of hours that the mother works does not significantly predict the child's IQ, whereas the mother's IQ is a significant predictor of the child's IQ controlling for the number of hours worked. And then we can get the effect sizes, so the standardized regression coefficient and the confidence interval for those standardized coefficients. And now we'll add an interaction term just like we did before. It's going to look a little bit different because we'll have some more information now, but the principle is the same. In terms of the code, right? We're just going to fit our model where we specify child IQ score as a function of mother's work, the centered version, and mother's IQ, the centered version, and we added that star because we want to add an interaction term. We'll fit our model. Take a look at the summary. And so here we see that when we add in this interaction term, that now that interaction is significant. So this tells us that the number of hours the mother works does moderate the effect of mom's IQ upon the child's IQ. And I want to say something real quick. Those of you who are not in the social and behavioral sciences, you probably are like, what the heck are you talking about moderation? You'll probably have heard this just referred to as an analysis of the interaction terms, right? I'm not sure if that's always the case, but I know that for the most part, moderation is specifically like a social sciences term from what I've seen. So basically, anytime I say moderation, I'm just referring to the fact that I'm saying that the effects of one variable vary as a function of the other. So please don't think that, if you've never heard moderation, this doesn't apply, right? No, this interaction terms are moderation effects, and moderation effects are interaction terms. So again, please don't let that scare you off if you haven't heard that term before. Okay, and so now we're going to probe the interaction, and that just means we're going to take a look at exactly what type of interaction we have. And so again, we're going to specify, this is actually something new. We're going to say sim slopes, and then we're going to say the name of our model. The predictor, again, is going to be mom's IQ, and this time the moderator is going to be the number of hours the mom works. And we're going to add a line of code that says JN plot. This is a Johnson-Neiman plot, and what it's going to do is it's going to show us at what levels of the moderator variable is mother IQ a significant predictor of child IQ. So we're going to look and see whether or not the significance of our main predictor varies based on the level of our moderator variable. So we'll go ahead and run this, and I'm going to maximize this so we can see what's going on. Let's take a look at the plot first. So what this is showing us is that down here on the bottom, we have the levels of the number of hours the mother works, and remember it's centered. That's why it looks like it runs to the negatives, right? Because 0 represents the average number of hours worked by mom. Same thing with IQ. 0 on IQ represents the average amount of IQ. And what we see here is that this turquoise is showing us that the slope for the mom IQ is significant throughout the entire range of mother's work hours. So regardless of how many hours the mother works, IQ is always a significant predictor of the child's IQ, okay? So this is just showing us, again, whether or not mother's IQ is still a significant predictor regardless of the range of the moderator variable, which is the number of hours mother worked. If there was a pink portion on this graph, that would show that there's only certain values or certain portions of our moderator variable levels at which our main predictor is a significant predictor. But in this case, it's significant across all levels of our moderator variable. And then the important thing right here, this is the really useful part, right? This is called the simple slopes analysis. And so what this is doing is this is looking at basically different levels of the mother's work. And so there's 3 different levels it's looking at. It's looking at 1 standard deviation below average in terms of the number of hours mothers work. It's looking at the average number of hours mothers work, and 1 standard deviation above average. And for each of these 3 levels of mom's work hours, it's looking to see what the slope of IQ is in terms of predicting child IQ. So we see here that the slope of mom IQ when that mother's work is 1 standard deviation below average, that slope is 0.73. But then that slope of mother's IQ when mom's work is 0, which is again is average because this is centered, we see that that slope is 0.61. And then now the slope of mother's IQ when mom's work hours are above average, the slope of mom's IQ is 0.49. So the slope of mother's IQ predicting child IQ is decreasing as mother's work hours increase. And we'll see that visually, and I probably should have showed the visualization first, but here we go. Okay, and what we see is exactly what I said. So the solid dark blue, this represents when mom's work hours are 1 standard deviation above average. And we see the slope is still positive, but it's to a lesser degree, right? It's not as steep. Whereas when we look at this really light dotted blue line, that represents when mother's work hours are 1 standard deviation below average, and that's when the slope is steepest. And again, this is the slope for mother's IQ predicting child's IQ. And so this slope, the magnitude of this slope, varies as a function of mom's work hours. So this is just an interaction or a moderation, the same thing. I mean, those terms mean the same thing. We are looking at the interaction between mother's IQ and mom's work hours. And we see that there is one, and specifically the relationship is always positive between mother's IQ and child's IQ, but the magnitude of that relationship or the degree to which mother's IQ predicts kids' IQ varies as a function of the number of hours the mom works. And this makes intuitive sense, right? If the mother works above average, then her IQ probably is less of a predictor of the child's IQ because she has less time to nurture the child and instruct the child. That would be my guess, right? Whereas when the mother doesn't work as much, then her increased IQ is going to pay more dividends, so to speak, because she'll probably have more time to instruct the child. Okay? And then the last thing we'll look at is we can also specify specific values of the moderator variable that we want to look at. So in other words, the plot that we just saw by default will look at +1 standard deviation, the mean, and -1 standard deviation in terms of the different levels of the moderator variable, or the first of the interaction variables. But you can also specify specific values. So because my mom's work is centered, right, I might say that I want to look at these 2 specific values of mom's work. I want to see what the slope is for mother's IQ predicting child's IQ at 2 specific values of mother's work. So I'll run that code. I had the wrong name, sorry. There we go. Oh, I've got too many plots going on. Let me clear that, run that again. Anytime you run your plots and nothing shows up, it usually means you have too much going on. Not sure what's going on. We'll just do this. Okay, sorry about that. And again, the same thing we saw before, it's just now I specified 2 specific values of mother's work that I want to look at the simple slopes for. And again, these are called simple slopes because we're looking at the slope of mom IQ predicting child IQ at a specified value of the other variable. Okay, so now that we've taken a look at how to run the code, the last thing we'll do is we'll look at our diagnostic plots. And so same thing as before, we get all of these plots in terms of whether or not our assumptions can be met But again, same thing as before. So now that we finally run all of our code, we'll go ahead and take a look at our PowerPoint at how we might write up and interpret these results, and I'll talk about why I center my predictors when I'm doing interaction or moderation. Okay, and so this represents that first model where we fit the main effects of child IQ as a function of mom's high school and mom's IQ. And again, we were not including the interaction term. And so all I did was I just put in the unstandardized slopes, the standardized slope, the p-values for the significance of those main effects, and then the confidence interval for the standardized slopes. And we see that this model explained 20% of the variation in child IQ, or sorry, 21% of the variation in child IQ could be explained by mother's high school and mother's IQ, and again, without an interaction term specified. But this shows us why we want an interaction term. What this is showing us is we see mother's IQ plotted against child's IQ score. And then again, we see that the darker color represents when the mother did not graduate high school, and the lighter lavender represents when the mother did graduate high school. And so as we can see, just like we saw previously, the slope is less when the mother did graduate high school. And then this is a histogram that shows the histogram of mom's IQ up here on the top with two different colors. So this is the histogram of just mother's IQ for the mothers that did graduate high school, and then the darker one in the background is the histogram of just mother's IQ for the mothers that did not graduate high school. Then over here we see the histogram of child IQ score only, and then the darker one is again for the mothers that did not graduate high school, and then this is the pink is the histogram of child's IQ for the mothers that did graduate high school. So this is a really powerful plot just because you can see both the bivariate histograms for both of your variables and the interaction that's going on all in one spot. Okay, but here's the important stuff. So this is a table with the regression results, but now with that interaction term added. And so we see again our unstandardized slopes, our standardized slopes, our p-values, and our 95% confidence interval. And this is actually the 95% confidence interval 95% confidence interval for the unstandardized slopes this time. It's up to you which you prefer to report. I usually report the standardized. I think for some reason I just chose not to. And now we see that when we allow this interaction term to be included, now we explain 23% of the variation in child IQ. So we explain more variation. Here's the important part though. So this is just an overview of what these terms mean, and then we'll talk about the specific values. So the intercept, when you have an interaction term, the intercept represents the predicted IQ for children whose moms did not complete high school and had IQs of 0. So in other words, the intercept is your predicted outcome value when both of your predictors are 0. Because we mean-centered mother's IQ, this is the predicted IQ for children whose moms had no high school and average IQ. And this is one of the reasons why mean centering can be powerful, right? Because now this intercept is actually interpretable, right? This is now the predicted IQ for kids whose moms didn't graduate college and had average IQ, because no one has an IQ of 0. All right, so the slope represents the predicted change in IQ between kids whose moms had no high school degree, so a high school equals 0, and average IQ, IQ equals 0, and the kids whose moms did have a high school degree and average IQ. So let me run through that again. Basically, the slope, once you've added interaction terms, the slope of the categorical variable represents the change in your predicted outcome between your two levels of your categorical variable, but it's only when your other predictor is set to 0. And this is why people like to mean center predictors when they're including interaction terms. Because again, not only is the intercept in terms of when the variables are 0, each of the main effects, so to speak, they're not really main effects, so I shouldn't say that, but each of the main slopes, so to speak, is interpreted in terms of when the other variable is at a value of 0. So if we mean center our continuous predictors, then now mom's high school slope is the predicted change in IQ between kids whose moms had no high school degree and an average IQ in kids whose moms did have a high school degree and an average IQ. And again, that's because we mean-centered IQ so that when IQ is 0, it's average. Otherwise, this would be the predicted change in IQ between kids whose moms had no high school degree and 0 IQ and kids whose moms did have a high school degree and 0 IQ. Similarly, mother's IQ slope, that's the predicted change in kids' IQ that's associated with a 1-point increase in mom's IQ when your categorical predictor is set to 0, so when mom has no high school degree. And then the interaction term, this is the difference in slope for mother's IQ for kids whose mothers did have a high school degree. And so basically, remember our regular mom IQ slope, that's the change in kids' IQ with a 1-point increase in mom IQ when the mom does not have a high school degree, so when the categorical variable is 0. So this interaction term represents the change in the slope when we do go to the other level of our categorical variable. So let's talk about what that actually means with our results. So our intercept is, this represents, where my cursor is, the kids whose moms have no high school degree and whose moms are of average IQ are predicted to have an IQ of 85.41. The slope for mom high school is the kids whose moms have an average IQ and a high school degree are predicted to have IQ scores that are 2.84 points higher than kids whose moms had no high school degree and average IQ. Because again, it's when IQ equals 0, and because we mean-centered, that's the average IQ. The slope for mom's IQ, that's for the kids whose moms have no high school degree. So when high school equals 0, each 1-point increase in mom's IQ is associated with a 0.97 increase in their own predicted IQ, or in the child's IQ. So I'll say that again. For the kids whose moms have no high school degree, so for the kids where high school equals 0, mom's high school equals 0, each 1-point increase in the IQ variable, the mom's IQ variable, is associated with a 0.97 point increase in their own predicted IQ. And then this interaction term represents for the kids whose moms do have a high school degree, each 1-point increase in mom's IQ is associated with a 0.49 point increase in their own predicted IQ. And where I got this from is we saw that the mom's IQ slope, when there is no high school degree, that slope was 0.97. Again, that's right here, because that's the slope of mom's IQ when the categorical variable is set to 0. All right, well, when the categorical variable switches in levels, that's our interaction. And so that slope for when the categorical variable was set to 0, which was 0.97, that slope now decreases by negative 0.48. So the mom's IQ slope when high school equals 1 is going to be 0.97 plus negative 0.48, which is 0.97 minus 0.48, gives us 0.49. So that's how I got that slope for the interaction represents that for the kids whose moms do have a high school degree, each 1-point increase in mom's IQ is associated with a 0.49 increase in their own predicted IQ. Basically, the slope decreases. The slope of mom's IQ decreases for the kids whose moms did go to high school, which we already saw from those plots. So again, I know it's a lot to verbalize, but the important thing is that we recognize that all that's going on is the slope of these effects is changing at levels of the other variable. And then here's our regression plot. So again, we're basically looking to make sure that there's no pattern to our residuals. This looks perfect. Our residuals are normally distributed around 0 for the most part, and we can see that through the histogram and the QQ plot. So our assumptions, our regression assumptions, appear to be reasonable. Okay, so now we'll talk about the interaction between the two continuous variables. So mom's work hours which were centered, and mom's IQ, which was, of course, centered. And so here were our slopes. This should be a little b, a lowercase b, sorry, and this is the unstandardized slopes. And this is the main effects, right, where we don't have the interaction term. So this is the unstandardized slope for the main effects. This is the standardized slope for the main effects. And this is the p-value for the main effects. And this is the 95 confidence interval for the standardized coefficients. And so we see that 20% of child's IQ is explained by mother's work hours and mom's IQ when there's no interaction term. And again, we see that mom's work is not a significant predictor control when mom's IQ is controlled for, but mom's IQ is a significant predictor when mom's work hours are controlled for. And again, these are the main effects because we left out that interaction term. And here's the plot that we saw before, and this is just showing that interaction, where as mom's work hours increase, the slope of mom's IQ predicting child's IQ decreases, but it's still positive regardless of mom's work hours. And here's the results. And again, I got all of these numbers just from that R summary that we already looked at. Again, these are the unstandardized slopes, the standardized slopes, the p-values, the confidence interval, and we see that we explain a tiny bit more of the variation, but typically that's not really as important as the interpretation, right? We're not too concerned about the increase in R squared that we get when we add an interaction term. We're more interested in what the interaction means and what it represents. And this is that same plot where we see that regardless of mom's work level, the slope of mom IQ predicting child IQ is significant across the entire range of mom's work hours. And one thing we can see too is that, see how this is sloping downwards? This is showing us that the slope of mom's IQ, because the slope of mom's IQ is actually what's on the y-axis. I forgot to mention this earlier. This is actually showing us that on the y-axis we have the slope of mom's IQ itself, and what this is showing us is that that slope decreases as mom's work hours increase. So that's why it's negative. It's showing us that the slope of mom's IQ as a predictor of child IQ, that slope decreases as the number of hours that the mother works increases, but it's significant across the entire range. And this black solid bar shows us what values we actually had in our observed data for mom's work hours, just so you can kind of see, you can pay more attention to the range that's most meaningful to you. Okay, and so here we'll go over the interpretation of our results again. So the intercept, again, that's the predicted outcome when both of your variables are 0, and because we centered them, it's going to be when both of our variables are at average levels. So it's the intercept is the kids whose moms work an average number of hours and have an average IQ have a predicted IQ of 87. The slope for mom high school, remember this is the slope for mom's, oh shoot, this should not say mom's high school, this should say mom's work hours, sorry. The slope for mom's work hours is for the kids whose moms have an average IQ, so when IQ equals 0, each 1 hour increase in mom's work hours is associated with a 0.5 increase in predicted IQ. So again, when you have an interaction term, each of these slopes is only interpretable in terms of when the other one is at a level of 0. So again, for the kids whose moms have an IQ of 0, which is average IQ in this case, each 1 hour increase in mom's work hours is associated with a 0.50 point increase in predicted IQ. And then for mom IQ, for the kids whose moms work an average number of hours, or when work hours is set to 0, each 1 point increase in mom's IQ is associated with a 0.61 point increase in their own predicted IQ. And again, this is why I like to center the variables, because it's a little easier to wrap my head around. And then the interaction term tells us the slope for mom's IQ, the slope itself, decreases by 0.1 for every 1 hour increase in mom's work hours past the average, right? And again, it's past the average because the average represents 0. So basically, another way of saying this is the slope for mom's IQ decreases by 0.1 for every 1 hour increase in mom's work hours past a work hour level of 0. And then this is I kind of worked this out here. So this says that the mom's IQ slope at an average work hour level, so when work hours are 0, mom's IQ slope is 0.61, and we saw that right here. The IQ slope at average work plus 1 hour, so when we increase 1 hour in mom's work hours, now that slope for mom's IQ goes from 0.61 to 0.51 because we subtract 0.1 from that slope for mom's IQ as we deviate away from when mom's work hours are 0, or when mom's work hours are average in this case. And the important thing to know too about interactions is the opposite holds true as well. We could easily flip this and say instead that the slope for mom's work hours decreases by 0.1 for every 1 point increase in mom's IQ, right? So your interaction can be interpreted in terms of whatever you think is most meaningful. This is why I don't like calling this moderation, because when you say moderation, you are basically theorizing that you're interested in one variable as a main predictor, and the other one is kind of like the levels at which you're like analyzing the effect of your main variable. But it can be either way, right? So anytime we're looking at moderation or interaction terms, you can look at this either way. It's not necessarily that you have to look at the effect of mom's IQ as a function of mom's work hours. We could also say, hey, the effect of mom's work hours on child's IQ varies as a function of mom's IQ. So the interaction holds no matter which term you're interested in as being your main predictor, so to speak, and which one you're interested in as being like the moderator or the variable that your main effect is dependent upon. So just want to make that clear. You can interpret this in terms of either of your predictors. And here's a quick summary. Mom's work hours moderates the relationship between mom's IQ and child's IQ. Mom's IQ is a significant positive predictor at all levels of hours worked, but the magnitude of that effect decreases with work hour increases. As mom's work hours increase, the effect of mom's IQ upon child's IQ decreases. Okay, and again, that's just because I chose to interpret this in terms of how mother's work affects the impact of mother's IQ on child's IQ. But I could have flipped this and been interested in the effect of mom's IQ upon the slope of work hours predicting child's IQ. And then the last thing is we'll look at our regression diagnostics. Here's a histogram of the residuals. They appear to be normally distributed around 0. Our QQ plot shows that as well. And then our residuals plotted against our predicted values. There doesn't appear to be any pattern. It's just a blobby little cloud, which is what we want to see. And then here's a plot of outliers. In this particular instance, I'm not going to pay too much attention, but I will note that there's a lot of points with high leverage, and then these green ones are identified as outliers because they fall outside of the studentized residual threshold of, I think it's plus or minus 3 or whatever they set it to. But regardless, it does look like we have some points that could be considered influential or outliers potentially, but I'm not too worried because it looks like our assumptions do appear to still have been met, but something you always want to pay attention to. So yeah, that's going to do it for today. I appreciate you watching the video, and as always, please feel to check out my GitHub page and like and subscribe. Thanks.